All right. So for today's notes, you're going to complete 7.2 radiocarbon dating and 7.3 old manuscripts. When we take a look at number or 7.2, you got two problems here, but there's a bit involved in these. Let's see. It says carbon 14 is used to find the age of certain artifacts and fossils. It has half-life or a half-life, which was one of our learning targets, of 5,730 years. So the half-life of carbon 14, which just means that it breaks down half of it, is almost 6,000 years. So if an object has carbon 14 in it, it loses half of it, half of that carbon 14, every 5,730 years. At a certain point in time, a fossil has 3 pictograms or a trillion of a gram. Big numbers here, big numbers, but don't really worry about it so much. But 3 pictograms or a trillionth of a gram of carbon 14. Complete the table with the missing mass of carbon 14 and years. All right, so first things first, we want to complete this table. Now, when we write out our function, what we know is, again, half-life is going to be, right, that 1 half here. Now, our y-intercept is always a. So our y-intercept here is 3. So we've got y equals 3 times 1 half. And now we know that every 5,730 years, right, that's whenever it goes down. So essentially, how are we going to get to the next one, right? Well, we don't know how long this is. We want to fill this part in, we want to fill this part in, and we want to fill this part in. So the way, if we start with, say, X, which is the number of years after a fossil has 3 pictograms of carbon 14. Well, don't we go from 0 to 19,010 by adding, 1,910. So did I add 1,910 to get to 5,730? No, not necessarily, right? So we added something else in there. We added that 3 times, or what would be considered 3,820. But then from 0 to here, we added the entire half-life cycle, 5,730. So we know 1 half-life has gone by between 0 and 5,730. So if it started at 3, 1 half-life circle has gone by. We just need to evaluate that in Desmos, or what's 1 half of 3, right? 1 half of 3 is 1.5, or 3 halves. So we were able to figure out that first one because 1 half-life circle has gone through. So you can see that equation there matches up. Well, what about this next blank? Because maybe I need that in order to figure out, right, this blank here with X. Well, in order to find here to here, how many times we went 1 half-life circle, but in this case, we did 1/3 of the time going through. What do you mean? Well, if I take, say, 1,910, which is the time passed from 0 to 5,740, and I divide it by an entire half-life cycle, 5,730, we're going to get 1/3. So that's 1/3 of a cycle that's gone by. 3 times 1 half to the power of 1/3. third. And now we can type that into Desmos to figure out what our next answer is. We just have 1/3 as our power. So 3 times 0.5 or 1/2 to the power of 1/3 is going to equal 2.38. And again, I got that by seeing that from 0 to 1,910 is a third of the cycle that I would have. So the exponent would have to be 1/3. Now, if I want to find out what this x is, this missing blank, what I know is that the result is 0.75. Using 3 as my initial value, 1/2 as the half-life, and x is our kind of missing unknown value there, right? So 0.75 equals 3 times 1/2 to the power of x. Or divide both sides by 3. And so if you divide both sides by 3, you get, what's 0.75 divided by 3? Looks like a fourth or 0.25. Let's leave it as a fraction because that kind of makes sense. Not a fraction, a decimal, 25. That's going to be equal to 1/2 to the power of x. So what would I need to put in the power of x to get to that, 0.25? So what would I plug in there, right? What fraction could I plug in? Well, how do I take a half and make it a half, right? A half of a half. I multiply it kind of by itself, right? Half of a half is 0.25. So that's one complete cycle. X is equal to 1 there. Well, we know one cycle goes from 3 to 1.5. So an entire 5,740 years has gone by. So all we need to do is add that back in to get 11,460. So that would be how we got to that next piece there. Okay. All right. If we move down here, it says a scientist uses the expression 2.5 times 1/2 to the power of t over 7,000 or 5,730 to model a number of pictograms of carbon-14 remaining in a different fossil t years after 20,000 BC. So what do the 2.5, the 1/2, and the 5,730 mean in this situation? So again, the 2.5 here is the initial value. So that's how much, how the mass of the carbon-14, right? If I go back up here, it's the mass of the carbon-14 in pictograms beginning at 20,000, right? The 1/2 is the half-life, and the 5,730 is the years that it takes. So 2.5 is the amount we start with. 1/2 is the half-life or the factor we multiply by. 5,730 is how long that half-life takes to take place. So then part B says, would more or less than 0.1 pictograms of carbon-14 remain in the fossil today? Explain how you know. So if we're talking about 20,000 BC, how much time has passed until 2020? Well, 20,000 BC, right? We go all the way to the year 0, then we add another 2020. So the amount of time that's passed is 22,020. So here we're going to put 20,000 plus the 2020 that we're at. And that means that the amount of time that's passed is 22,020. So how many half-lives have taken place since 22,020, right? Well, we divide that by 5,730 because that's how long one half-life takes. I would use maybe your Desmos calculator for this. Divided by 5,730, I get 3.84. I'm just going to round it to the nearest hundredth. So let's say 3.84 half-lives have taken place. So at that point, that's our new exponent, is that 3.84. In which case, what we're going to do is now plug that in to the function. We'll say that this scientist has 2.5 times 1/2 to the amount of half-lives that have taken place, 3.84. Now, we could have put that 22,020 in for t. We already did that. That's t, right? We just have our 3.84 now. And I'm going to type that into Desmos. 2.85 times 0.5 to the power of 3.84. And I get 0.17, 0.18. I'll round it to 0.18. So when it says is more or less than 0.1 of a pictogram remaining in the fossil, more. How do I know? By the math that I just did. Okay. All right, let's move down. That's all of 7.2. I'm going to move down here to 7.3. The half-life of carbon-14 is about 7,000 or 5,730 years. Pythagoras lived between 600 BCE and 5,000 BCE. Explain why the age of papyrus from that time is a half-life of is about half of the carbon-14 half-life. So when we're looking at this, we're looking at 6,000, 5,000, or excuse me, 600 BCE, 500 BCE. When we try to determine why it was about half of the half-life, what we know is that we've got 600, we'll just go 600, for example, plus the 2020 that we're living at. So we'll call that, and it does say about, right? It says about here. We're going to call that 26,620, right? So we know that the half-life is 5,730. So if I take that and divide it by 5,730, our answer, what I'm looking for is about half. And what we're going to get here from this division is 0.46. So that's about 0.46. Now that's really close to a half of the half-life. That's where we get confused. It's not saying that it is a half-life. It's saying that it's about half of the half-life, so a quarter of it. And so that's correct. So the age of papyrus from the time of Pythagoras is about half of a half-life. So it's deteriorated a fourth of a half-life. Okay. All right, number 2 here says someone claims that the papyrus scroll written by Pythagoras, they have it. Their testing shows that the scroll has 85% of the original amount of carbon-14 remaining. Why is this likely to be a fake? Why are the people claiming that they have a scroll from Pythagoras lying? Well, so what we should know here is that after half of the half-life that we just figured out is remaining, what we should do is say, all right, well, what percentage of the remaining would be there, right? So if I had 100%, say 100%, times the half-life to a half cycle, what am I going to get? Well, 1/2 to the power of 1/2 is about, we'll call that 0.71 or 71%. So the reason we put a 1 there, we could have put a 100 for, right, that's the amount. Essentially what we're saying is that it has all of its carbon-14 when it was written, right? All the carbon-14 that it has. But the scroll now has 85% of it. Well, according to the math, if we did the time zone that it took, which would be a half of the half-life, we get 71% of the carbon-14 should be remaining. They have 85%, so there's no way that should be technically the real thing, right? They should have less carbon-14 in it than what it's saying. All right. Last question here says a copy of the Gutenberg Bible was made around 1450. What would more or less than 90% of carbon-14 remain in that paper today, and explain how you know. We're going to use the same half-life, 5,720, for this one. So for this Bible that was made around 1450, how much time has passed? So 2020 minus 1450. So what do we get there? 2020 minus 1450, 570. Let me just do my 7 there. 570 divided by 5,730. That will give me a fraction. That's going to be my exponent. So let's see. That should be about point. We'll call that 0.1 or 1. Yeah, 0.1. We'll call that 0.1 because that's about a tenth of the time that it's taken. So would more or less than 90% of this be remaining? Well, we know that we've got a tenth of it, so we're going to say 1/2 to the power of 0.1 to determine what the factor would be, and that's going to be a roughly 0.93 or 93%. So it looks like more than 90% would be remaining. Okay, and you don't need to know how much was in it. We're just talking about percentages. So if you were to say multiply that by 100% or 1, it would give you about 0.93 or 93%. So more. All right, there's your notes. Turn it